All right. I promise that this is the last time we're going to talk about some of this stuff for today. But I just wanted to go through a last couple of slides. Last time we sketched both a probability density function or distribution function and also a cumulative distribution function, both of which came from this PDF right here. You know, what two buses, who cares, right? I mean, in the end, this is the thing that we were thinking about. And the reason why I wanted to talk about this is because we have the graph all nicely drawn on here. And by the way, so you can always stretch these things out. Like if I grab this and pull it over, I can see the whole thing. Do you see how the graph kind of like automatically scrunches itself up when you do that? So that if you do that, you can see the whole definition of the CDF, which is capital F, and the PDF, which is little f. And there's kind of an interesting relationship going on between the two of these, which we talked about last time. Of course, that's not surprising because the cumulative distribution function is gotten from the density by simply integrating the density up to some point. Okay, that's how the cumulative distribution function is obtained. Okay, so we'll come back and look at this in a minute, but I just want to go through a few slides here. So here's another example. Let's let X denote the amount of time a book is actually checked out at the library, and suppose the CDF is given by that formula right there, that formula right there. Well, how would you compute the probability that X is between 0.5 and 1? How would you compute that? Well, remember, you don't have to be too concerned with equals at all. That's one reason why. I mean, it shouldn't surprise you. We'll come back to this in just a minute. It shouldn't surprise you that over here in Desmos, look, the CDF is continuous. Do you see this? The CDF is continuous. And remember, the cumulative distribution function is adding up probabilities as X gets larger and larger and larger. So it can never happen, never. It can never happen. Let me say that again. It can never happen that the CDF jumps at a given point. Because what would that mean? If the CDF ever jumped at a point, that means the probability of being equal to that point is positive, which never happens for a continuous random variable. So for a continuous random variable, the CDF is continuous. It is continuous. It's a continuous function if you sketch it. That's because it can't jump. As I move X from left to right, as I let it get bigger and bigger, there's no probability concentrated on a single point. So the thing can't jump in probability. And so that's why this thing is continuous. It's beautiful. Look at this thing, this little S curve right here. So back to this. So we don't have to be super concerned about equal signs because we're a continuous distribution function, but the probability that 0.5 is less than or equal to X, and that in turn is less than or equal to 1, well, isn't that just going to be the cumulative distribution function evaluated at 1? Now, the cumulative distribution function evaluated at 1, that would be the probability all the way up to 1. That would be the probability that X is less than or equal to 1. That's too much. So we need to get rid of the probability below a half, but that's just the CDF of F evaluated at 1/2. Okay, so it's capital F of 1 minus capital F of 1/2. Okay, I know I'm not really writing this on the board or anything, but you know, it's fairly straightforward to do this. So it's the cumulative, the CDF evaluated at 1 minus the CDF evaluated at a half. That's how you would get that first probability. So what is the CDF at 1? Well, you would have to use the second definition right here because, for x's between 0 and 2, which 1 is, you would plug into this one. So f of 1 is 1/4 times 1 squared. Okay, minus. So where's 1/2? Well, 1/2 is also in here, you understand? 1/2 is also in here. So that'd be 1/4 times a half squared. Okay, so that's just going to be 1/4 minus 1/4 times a half squared, which is also a fourth. Okay, so that's like a fourth minus a 16th. You should be writing this down to kind of keep track of what's going on. So that's a fourth minus a 16th, which is 4 minus 1 over 16, which is 3/16. Okay, so that first probability is 3/16. Now, what about the probability that x is bigger than 1.5? Well, that's 1 minus the probability that x is less than or equal to 1.5. Okay, which is 1 minus the cumulative distribution function evaluated at 1.5. And you say, all right, that's 1 minus, okay, I have to compute the CDF at 1.5. So which of these do I use? The middle one again. So that's going to be 1 minus a fourth times 1.5 squared. Okay? Which is 1 minus 1.5 squared is 2.25. 2.25 all over 4. So this is 1 minus the fraction 2.25 over 4, okay, which is 4 minus 2.25 all over 4, which is 1.75, 1.75 all over 4. Okay, whatever that is. Let's just leave it at that, okay? We have the answer. So it's 1.75 all over 4, okay? So we can use the CDF to compute probabilities just like we could in the discrete case, but we don't have to be so overly concerned about being equal to any number, okay? So that's kind of an advantage. Okay, so the answer to this first one is 3/16. The second one is 1.75 over 4. Okay, so yeah, let's move on. And so this is kind of what I wanted to get to. Says if x is a continuous random variable and the PDF is little f of x and the CDF is capital F of x, then at every x at which f prime of x exists, capital F prime of x exists, it turns out that the derivative of the CDF is the PDF or the density. And that makes sense because remember, how do you get the CDF from the PDF? Right? So that's the opposite of what we're talking about here. So here we're trying to get the PDF from the CDF. How do you get the CDF from the PDF? Well, you integrate it all the way up to x. So it makes sense that the CDF, if I take the derivative, I would just get the thing that I'm integrating. That's actually called the second fundamental theorem of calculus. Okay, and so that's not that surprising that the derivative of the cumulative distribution function is the density. Okay, that's what this identity is right here. Okay, so that's interesting. So if we go back to this graph over here, this red curve right here is the derivative of the blue curve. The blue curve is the CDF, the red curve is the PDF. If I were to take the derivative of the blue curve, I would get the red curve. I don't know if, let me see. Can I just go f prime of x? Ooh, That's nice. It knows. I've already defined capital F of x, and it's that blue curve. Actually, I knew it was going to do that. I don't want you to think that I'm discovering things as I'm going here. But that's really affirming that when I took the derivative, okay, let me just erase that again, just so you see it disappears. The red curve is the density, the blue curve is the CDF, and watch what happens. Capital F prime of x is the green curve, and it's right on top of the red curve. Yeah? So the derivative of the CDF is the PDF. Okay, so that's a really handy thing to have in our back pocket. Okay? So going back to this example back here, what I'm asking for is the density function, little f of x, for this example. Okay, what is the density function for this example? Well, okay. How do I get the density from the CDF? Well, I take the derivative. Okay, I'm going to take the derivative. So let me just, let's actually put this over in Desmos and do that, So I just wanted to do that here. So I go over to Desmos. Let's do a different letter. Let's do, capital G of x equals, okay, I can shut these off. So here I'm shutting things off here. If you click on these things, you can shut them down. So I said that for x less than 0, this thing was 0. For 0 less than or equal to x less than, okay, what was it? 0 less than or equal to x less than 2. Okay. Less than 2, what's going on? It was 1/4 x squared. All right. And oops, what in the world am I thinking here? I need to put a colon. Yeah. That was how we were doing this before. And then for 2 less than or equal to x, what is this? Oh, right. For x equal to or greater than 2, we're just 1. That's it. Okay. Let me just say for x equal to or greater than or equal to 2, it's 1. There it is. There's our thing right there. Okay, and of course, if I want the density of this thing, look, this behaves like a CDF. Look, it's always going up from left to right. It's 0 if I go to the left. It's 1 if I keep going to the right. If I want the density, I just have to take the derivative. Capital G prime of x. There it is. There's the density right there. So it goes 0, and then it's like that. That's just the derivative of this middle guy right here. And then it's 0 from that point on. The density, right, is the thing we integrate. And I can't be, the area under this thing right here, let me get rid of the purple guy for a minute. The area under this thing right here needs to be 1. You know what I'm saying? The area under this thing needs to be 1. And it's 0 outside of the interval from 0 to 2. And look at this. What's the area of this triangle? Well, it's going to be half. Look at this. This is a rectangle of base length 2 and height 1. So the area of this rectangle is 2. Half that is 1. So indeed, the area under this curve is 1. That's just a straight line. Okay, because look, watch this. Let me get rid of this. Let me define little g of x as the density. This is equal to, I'm just going to draw this in a piecemeal way, and you'll see it's actually straight up equal to the derivative of the cumulative distribution function. For x less than 0, what is it? Well, what's the derivative of the 0 function? It's 0. I'm looking up here at this. What about for 0 less than or equal to x less than 2? What is the derivative of 1/4 x squared? What's the derivative of that? Well, the 2 comes down, it's 1/2 x. Oops, x. Okay? And then what about for x equal to or greater than 2? Well, what's the derivative of the function 1? Well, it's 0. There it is. There's the red curve right there. Okay, and that is exactly the same as the thing we got when we took the derivative. That's exactly the same thing when we got the derivative of this cumulative distribution function. Isn't that amazing? Okay, same exact thing. Okay, so that's fascinating to be sure. Okay, so we found that density. We actually have what it is over here. I put F, but over in Desmos I used little g for it. This is what it is. It's 0 before 0, it's 1/2 x between 0 and 2, and it's 0 after 2. Okay, so that's the density of that thing. Okay, and that's really all I wanted to say during this lecture. I know it's been kind of a long thing. Still getting the hang of this. Thank you guys for being gracious. I know that this isn't ideal, but man, let's just we're in this together. Make sure you ask questions. Make sure you stay in touch. I'm going to send out an invitation for Zoom. Every day for office hours and for class time, I'm going to have Zoom. That means you can actually talk to me in person through your computer. So just hang in there. We're in this together. Ask questions. It'll be fine. The Lord will use this to help shape our hearts and in ways we could not have anticipated. So that's all for now.